a timeline? We do a timeline because people look at this and they say, well, this isn't possible. What we have to think about when we're thinking about the fact that a bunch of small changes can add up to a difference like this and this is how long the scale of time is that we are talking about. Because humans can't wrap our brains around this. Is it any wonder? I mean, look at where we are. You know, modern humans are in the last, like, half a centimeter of this thing. Look at how much time has elapsed prior to us.
The 3 billions were rough.
The billions are rough. And I mean, it's a huge, long history prior to us showing up. We have a hard time conceptualizing that. Mr. Schneider, the old retired science teacher who was subbing for Mr. Andres yesterday, he was watching you guys. He came out and he said, you know what irritates me? On the weather news, they'll say, it's the worst hurricane ever. How do they know that? We've had weather for a long time. Yeah, it's true. We tend to contextualize things in our own lifetime, and our lifetime is a blink of an eye. And, I mean, the universe is even older. The universe is 14.2, 14.3 billion years old. Whoa.
Well, I thought it was... No, never mind. I guess I thought it was 2,000 years.
No, that's current era. That's current era. Okay, so this is a big span of history, and that's why I have you do this, to try to get that concept across. So if you feel like you were tortured a little bit, if you feel like you did more dividing by tens and ones and hundreds than you would have liked, the goal is that you get what kind of span this is. And I don't have a better way to get that. And if you think the end of the year, when I do my end of the year feedback, and you will actually do a form for me, and I will say, you know, what'd you like the best, what'd you like the least, what worked, what didn't work. If you have come up with some better way to get this idea across, tell me. Because I do modify curriculum based on what student feedback I get. But this is a huge, long span of time. It's incomprehensible to us. So I can stand up here and say, you know, the span of Earth history is really long. But you don't get it until you see it visually and you create it. And so I think that's important. So we're talking about this in the context of evolution of life on Earth. The Ohio State Standard is this. The diversity of living things on Earth results from billions of years of biological evolution. That's the state standard. And they test that extensively on the air test at the end of the year. The Earth is about 4.6 billion years old. That number has not changed. And you did a little bit of reading that talked about how we know that, because that's another question that people come up with is, well, how do they know it's 4.6 billion years old? And they can look at the actual chemistry within rocks, within minerals. They've looked at moon rocks. They've looked at the oldest rocks found on Earth. And they do some really good chemical dating based on how those rocks do radioactive decay over billions of years. So that's a pretty fixed number. This one's a little bit more in flux. So 3.5 billion years ago. So where is 3.5 billion years ago? Now this I think is according to your textbook. Here we say 3.8 billion years in the past. There have been scientists, even in the last 5 years, who have found things and said, oh, we got to move this date. Oh, we got to change this date. Because remember, science is tentative. When we get new information, we revise what we say is correct. And, you know, could there be older fossils than that? There could. There was one about 3 years ago, and they said, hey, we found new fossils in Greenland. We push back the date on the first living things. They were pushing it back by a couple 100 million years. And then just in the last week, other scientists looked at their work and said, no, you were mistaken. And so now we're in the process of, not we, I'm not involved in this, but the scientific community is in the process of looking at those results. So, you know, can this number shift a little bit? Yeah, it can. It's not going to get any further forward. This is pretty fixed. Could it be a little further back? Yeah, it could. That's only 1 billion years after the planet forms. What does the early Earth look like? Is this a nice place to live?
Yes. No.
No, it's a ball. So you've seen pictures of lava?
It's a lava line.
This is a ball of hot molten rock. There are no oceans. I mean, this picture is not even doing it justice. There are, yeah, I gotta fix the picture. There are no oceans. There's no real oxygen in the atmosphere. It's molten rock. Nothing can live there. It's got to cool down first. Why is it molten rock? Is anybody wondering, like, well, why is it molten rock? But where did the inner core come from? Why? I mean, the core doesn't even form. I forget where that happens in geologic history. Do you know how this was formed? How was this formed? You ask? I want everybody to take, oh, you know how much I love having you smash your fists together. Go ahead, make a couple of fists. Jazz hands. Lots of asteroids. The early solar system is full of little objects flying around. Has anybody here ever played paintball?
Yeah.
Okay. I have not, but I have watched some of my dear friends get pummeled. And watching, I have a very clear image of my friend Kimmy running across a field with like 43 people firing on her. No, it was like 2. But it looked like 43. And she was just getting the crap beat out of her. And she came back just covered. It was kind of like she said, I quit, I got to go to the bathroom, and they all said, fine. And they just nailed it. Yeah, that's kind of what the early solar system was like. A flying hail of little tiny objects. Well, some of those little tiny objects start to stick together. Go ahead, do it. They start to stick together. And the more of them stick together, okay, we'll pause now. The more of them stick together, the bigger the clumps get. And the bigger the clumps get, the more gravity they have, and the more they start to pull things into them. And pretty soon we've got these massive, rocky, molten, smashed. It's like taking Play-Doh and mushing a bunch of it together until you got a big gob of Play-Doh. It's hot. It's inhospitable to any life. There are no oceans. There is no oxygen. It's a mess. You wouldn't want to live there. You might not even want to visit. It's pretty awful. But, you know, by the time, a billion years in, or less, it's cooled down enough, and we've got oceans, and we start to see the first evidence of living things. What do those first living things look like? Who looked up pictures of the first fossils? Do they look like anything you recognize?
No.
No. So who has a dog at home? Excellent. Have you ever looked at the dog's water dish?
Yeah.
Exactly. There's that slimy film on it. Oh, my mom is so freaked out by dog water dishes. Like, she won't even, if she touches it, she has to go wash her hands in the laundry room. She won't even do it in the kitchen sink. She's a little over the top about it. But that slime is what we call a biofilm. So I'm going to shrink this. You might want to write this down. So when you get layers, what is that slime on the water dish?
Bacteria.
Well, it's actually interesting because it's not just bacteria. It's kind of like bacterial cities. So bacteria build these mats, and we call them biofilms. These are a huge problem in medical applications. If you've ever known anybody who had a catheter, ooh, yeah. My dad had one towards the end of it. A catheter is a tube that they shove up your urethra, and it connects directly to your bladder, so you no longer pee like a normal human. You pee into a bag because the pee just runs out the tube from your urethra. So for people who are in medical comas, for people who are handicapped in a variety of ways, like my dad was bedbound when he was at the end of his life, he had a catheter. And one of the things you have to watch, and I mean, you don't want to have to ever do this, is making sure that that catheter tube isn't building up a biofilm. Because that is clusters and clusters and clusters of bacteria. They sort of create their own surface. It's kind of like if I come over here and I climb on your shoulders, and then Dylan climbs on my shoulders, and we make this sort of pile. That's what the bacteria do. They form these biofilms. Biofilm. And it's all these mats of bacteria standing on top of one another. So an individual bacteria is not going to leave you a fossil. It's not going to happen. However, when we get enough layers of bacteria, we start to see fossil evidence, and they're called stromatolites. They're found off the coast of Australia, and they are layered evidence of early biofilms. And if you look at them at a very, very detailed level, you start to see some structures that tell you, oh, okay, that's what these were. But those, I mean, these don't look like living things to us. It looks like, somebody took crayons and drew a bunch of lines on a rock. But it's actually fossilized, sort of biofilm mats. It's pretty disgusting. I like to think of it, actually, because I like making the world as disgusting as possible. As fossilized dog water bowl slime. Ew. You're welcome. It's not until about 600 million years ago that animals even show up on the scene. And where do we have first evidence of animal life? Complex organism. Yeah, 540 million years ago, first abundant life in the fossil record. And somebody said to me today, is that even an animal? Oh, they're freaky. These are weird looking things.
I'm not seeing anything.
Those are animals.
Eh?
Huh? Exactly. Exactly. They don't look like what we think of as animals. I mean, first of all, we have a bias. We all need to admit that we have a bias. We are mammals, and when I tell you to name 10 animals, I can bet you money. If I don't tell you this beforehand, you're going to name 10 mammals.
Dog.
Yeah. You're going to go dog, cat, coyote, raccoon, cat, cow, sheep. Those are all mammals. Expand your horizons. You would say, okay, we might throw in a reptile or an amphibian. We might throw in a turtle or a frog. It's a mammal. That's a mammal. Birds are aves. Okay. But in general, we have a bias. We think of animals as looking a little bit like the animals we're familiar with. 600 million years ago, these things looked like sponges and feathers and like weird, crazy stuff out of a science fiction movie. 600 million years ago, this is what animal life looks like on Earth. Now, and if we go, we are going to go to the Carnegie after Thanksgiving hold, and you can look for some examples of primitive animal life because they have got a great fossil collection there. That's a really good question. Is this underwater? Yeah. So, remember homeostasis?
Yes.
What are the two things you got to control?
Temperature and wetness.
Wetness, yeah. Water balance. Well, if you're out on land getting baked, if you're getting cooked by that sun, it is hard to keep your moisture in. Who here has dehydrated on a hot day? I have! And we've got systems in place to prevent that. These poor little critters wouldn't stand a chance. You put them out on a sunny rock and you can eat them later. Because they're going to be all shriveled up and dead. I'm serious. I don't know how they would taste. That would be really interesting. Eating your way through the Precambrian? I forget which era this is. But anyway, when you are not in the water, it is much harder to maintain both your temperature and your water balance. So most living things evolved in water and eventually made the move to land. So, okay, we get animals 600 million years ago, freaky, weird animals that don't look like anything we can think of, and then, lo and behold, mammals. That's mammals. That's a mammal. It's not us, but it's an ancestor of us. That is one of the first mammals that shows up in the fossil record. And it's about this big. It's adorable, isn't it? It's not a dinosaur. It looks a lot like a rat or a shrew or a ferret, and those are all mammals. It's furry. It gives birth to live young. It nurses its young. It's got teeth. It's got a vertebrate skeleton. It's got a backbone. I mean, it's got a lot in common with us, other than the fact that it's this long and it looks like an ugly prehistoric rat. You know, minor differences.
So what is it?
It's an early mammal. I don't know the species name.
Oh, okay.
When we go to the Carnegie in November, they actually have one of these in the exhibit running around the dinosaur's feet.
Oh, I thought you literally meant running.
No. It's a model. It's a model, just like the dinosaurs are. But they have a skeleton of this thing, and then they have a reconstructed model. So I usually offer like a bonus point if you can find the mammal in the dinosaur world. So, you know, at the time that this thing lives, 300 million years ago, it's in competition.